In this lesson, we're going to look at the calculations associated with those transitions in hydrogen atoms. This diagram shows all of the transitions that can occur in a hydrogen atom. The Lyman series is in the UV or ultraviolet region. The Balmer series is in the visible region. So this is what we can see with the naked eye. And the remaining are in the infrared region, so lower in energy. To do these calculations to find the wavelength associated with a particular transition, we're going to use what's called the Rydberg equation. And in this equation, we have 1 over lambda. So this is the wavelength, and we need to have that in units of meters. We have the Rydberg constant, which is 1.097 times 10 to the 7th inverse meters. We have N1 squared, and N1 is the initial energy level, so wherever the electron is starting. And this works whether we're dealing with an absorption or an emission. N2 is the final energy level, so the final spot for the electron. That can be the excited state or a ground state. And what we see is when we get done, we get a positive wavelength that indicates that we have an absorption occurring, and a negative wavelength is that there's an emission. Because wavelength is a distance, it can't actually be a negative distance. The sign simply tells us whether we're getting an absorption or an emission. Let's look at an example. Calculate the wavelength of the radiation emitted by a hydrogen atom when an electron falls from the n equals 3 to the n equals 2 orbital in the Bohr model. We're going to start by putting down our Rydberg equation. 1 over lambda equals RH times 1 over n1 squared minus 1 over n2 squared. We have 1 over lambda equals 1.097 times 10 to the 7th inverse meters. That's our Rydberg constant. Now I'm going to plug in my energy levels, and we're starting at n equals 3 and going to n equals 2. So we have 1 over 3 squared minus 1 over 2 squared. I get 1 over lambda equals Rydberg constant times negative 0.1389. I multiply that by Rydberg's constant and get minus 1.524 inverse meters. Now I need to take the inverse of both sides. And when I do that, I get lambda equals minus 6.56 times 10 to the minus 7 meters, which is also 656 nanometers. The negative sign indicates that this is an emission. We don't actually have negative wavelengths. Identify the transition to the n equals 2 orbit in the Bohr model that gives rise in the emission spectrum of the hydrogen atom that has a wavelength of 410.1 nanometers. In this case, we're told where the electron is going to, but we don't know where it's starting. However, we do know the wavelength. We're going to use Rydberg's equation again, and we're going to convert our wavelength from nanometers into meters. The wavelength in the Rydberg equation must always be in meters. I have 1 over 4.10 times 10 to the minus 7th, and that has a negative sign in front of it because we're dealing with an emission, equals Rydberg's constant times 1 over n1 squared. We don't know where we're starting, but we do know where we're ending, so we can plug in the 2 there and get 1 over 2 squared. On the left side, when we take 1 over 4.10 times 10 to the minus 7th, we get 2.439 times 10 to the 6th equals Rydberg's constant times 1 over n1 squared minus 1 over 4. I'm going to divide both sides by Rydberg constant, and we get minus 0.2223 equal to 1 over ni squared minus 1/4. I'm going to add 1/4 to each side, and we get 0.0277 equals 1 over ni squared. And that gives us 36.1 equals n1 squared. N1 equals 6.01, which we round to 6. In this case, our transition is going from the n equals 6 orbit to the n equals 2 orbit. Still both in the excited state, but we've emitted energy and gone to a lower energy excited state. Calculate the energy of the electron in the hydrogen atom if the electron transitions from an n equals 4 to n equals 2. We're still going to need the Rydberg equation, but we're also going to need to find the energy, and so we'll need to use E equals hc over lambda because that's the relationship between wavelength and energy. Now we're going to plug in the values into our equation. We don't know lambda, we do know Rydberg's constant. We know we have 1 over 4 squared minus 1 over 2 squared. because we're starting at the 4 level and going to n equals 2. We then get Rydberg's constant times minus 0.1875. We multiply those and get minus 2.057 times 10 to the 6 meters. We need to take the inverse of both sides, and we get lambda equals 4.86 times 10 to the minus 7 meters. But we're trying to find energy, so we need to take lambda and plug that into the other equation. E equals 6.63 times 10 to the minus 34th joules second, so that's Planck's constant, times the speed of light, 3 times 10 to the 8th meters per second, over lambda, our wavelength that we calculated, 4.862 times 10 to the minus 7th. And we can solve that and get 4.09 times 10 to the minus 19th joules.